Good afternoon. Okay, nice to see a full hall for now. We'll see how that goes. So, in case you're wondering where you are in operating systems. Let me make sure, is this actually recording? It does seem to be recording, that's good. So, first off, I record my lectures, I put them online. Out of curiosity, how many of you would be interested if I live stream this? Just out of curiosity. Okay. Yeah, I thought so. So you can stay at home and kind of watch it. Yeah, exactly. Okay. I have my own reasons for wanting to do it, but anyway. So first off, yes, I put these online. The place, if you're looking for material for this course, you should all have access to See You Learn. You should have all been able to, you can get into theirs, access that, and then there is my wiki. And if you look at my wiki, you'll go to the main page, and then you go here, and then you go here, the notes, and oh, here's information on the class, and here's the course outline. So this is the first day of class, so I guess we should discuss this. You're operating comp3000, comp3000B. I should probably make it say that technically. My name's Anil Somayaji. Unless you tried taking this class already, I probably have not seen you in class because I seem to normally teach this class and various fourth year classes, distributed operating systems, and what else do I teach? Oh, yeah, I've taught computer system security, and I've taught various other graduate seminars, although none of those in the recent past. So we had 9 teaching assistants for this class. There's 251 students signed up for this class last I checked. I'm not sure what it is now. We had 9 TAs. We're down to 8 because one of our TAs was in SCE, and SCE pulled their TAs, so we don't get them anymore. So he was good, but I'm not sure. I think this TA list may be changing. We'll see. The thing you should know is that there's lectures and there are tutorials. Oh, I have to take him off here. You see him there. But anyway, for the tutorials, there are 4 tutorials. Actually, there are 5 in the schedule. There is one tutorial that was set up for Tuesdays from 7 to 8:30, and nobody was signed up for it. I'm not quite sure exactly why no one was signed up for the 7 to 8:30 p.m. one, but 50-something people were signed up for the Wednesday 8:30 a.m. one. I don't quite get that. But that's apparently what the system said. If we have the 5th tutorial from 7 to 8:30 in the evening on Tuesdays, we potentially could run that. I really don't want to run an extra tutorial. Well, the TAs really don't want to run an extra tutorial if they don't have to. But we'll figure that out for next week. Tutorials start next week, so you don't have to worry about this week. Tutorials start next week. Office hours for the TAs will start for next week. We should get all that organized. This is the web page. And in terms of what the course is, this is, the official description is operating system implementation course stressing fundamental issues in design and how they relate to modern computer architectures. Assignments involve the modification and extension of a multitasking operating system. So, what's that mean? I expect we're going to hack on Linux. You might say, well, we'll talk about why does Linux make sense to hack with it, but yeah. What I expect you to be able to do at this end is be able to write C code, understand how something works, have a conceptual model, and understand something about virtual machines as part of it, because it turns out it fits rather nicely into the topics of this course and is rather relevant for things going forward, because I suspect most of you will be doing something with the cloud, probably. So if you are, you should understand what virtual machines are. Yes?
For Linux, can you just make the example that I have the image from Linux's website, the virtual image that I'm running? Is that okay, or do we need the code specific?
So do you need a course-specific image, or can you just use your own Linux image for doing stuff for the course? You are welcome to use your own. I use Ubuntu. I'll be using Ubuntu 18.04 for this course. If you want to use Arch or Gentoo or whatever else, it's fine. I will not have tested my code to run on your Linux distribution. It is possible the code may break. It's even possible potentially for you to run the code from this class on Windows and Mac OS. On Mac OS, it's a little bit easy. Well, Mac OS is a Unix variant, so a lot of the stuff works, but actually there's some subtle differences. On Windows, Windows now offers a Linux subsystem, so you could actually do a lot of stuff on Windows, but again, maybe saying. So if you want to see how things work or not work, you know, it might work, it might break, but just beware. You know, that's, and I mean, it depends. I mean, if you're feeling a little nervous about this course, don't do it. But if you've been playing around with Linux for a while and are comfortable messing with things, and, hey, go ahead. No problem. Grading, because I got to give you a grade. I know. So the 20%, 40% of your grade is from the tutorials and from the assignments. 60% is from the midterm and final. Actually, I need to change that. That shouldn't be 30-30. That should be 25, and 35. Yes, because the final is supposed to count for more. I forgot. That was a leftover from before. So the key thing to understand about the tutorials and assignments in relation to the rest is basically 2 tutorials are the material for 1 assignment. And then the midterm is the first 2 assignments, and the final is the material from all 4 assignments. So if you learn things in tutorial, you are set up for the assignments, and if you understand the assignments, you're set up for the midterm and final. If you slack off on some of these things, you know, I get you. I mean, it's like if you decide to just fake it for the tutorial participation and the assignments, you can, but then you're really going to do really badly for the other 60% of the grade. I find that students who put in an honest effort for these other parts do okay for the rest. So even if these are, in some sense, a little more participation grades, that's actually what's required. You have to try. Now, one thing I'm going to do a bit differently this semester is in the past, I've treated tutorials as a participation grade. Basically, you show up at the tutorials and do the things and kind of attempt to do some work, and we give you marks. Some people in the past have slacked off a bit on that. So what I'm doing this time is assigning each of you a TA. Based on your section, you will have a TA that you report to. I think we're going, this is the first time doing this, I'm not sure. We're probably going to switch around who you report to for the second half. But the idea is that to get your participation marks for the tutorials, you have to convince your TA that you've made an honest effort. And in other words, if you just sit there and just click a few things, no, they're not going to give you full marks. But if you sat there and really tried to learn the material, you'll get full marks. You don't have to understand everything. Understanding is tested later on. I'm looking in the tutorials for you to put in the time. Because if you put in the time, you typically learn. If you don't put in the time, So basically, show up for the tutorials. If you don't want to show up for if you can't show up for a given tutorial, that's okay. You just have to make sure you talk to your TA and talk to them separately. You could email them. They probably will want you to actually meet them in their office hours. But you can work with them to get, credit for those, for your tutorial time. But do that. Don't skip out in the tutorials, because that's the basis of everything in this class. There's a wiki. There's also course discussions on CUlearn. If there's things you want to contribute to some classes, that's more in the past, not so much now. One thing I do want to talk to you about is collaboration. I know you all work together. I think it's generally a good thing. what I want you to do when doing your assignments is if you work together, tell us. Tell me who you're working with, and preferably which questions and stuff. Let me know what online resources that you use for answering questions. We want to know what resources you're using so that if we find you're giving wacko questions, but you're using a legitimate resource, we go like, okay, fine, we can give you credit for that, and then tell you, no, that was wrong. Collaboration is fine on the assignments. Just tell us. Collaboration is not okay on the midterm and final. Those are individual things. Now, one strategy for collaboration on assignments is divide and conquer. It's like, oh, question 2 seems really hard. Why don't you do that one? I'll do question 3, and then we'll combine our answers together and have the assignment done. Don't do that. That's a really bad idea. It's a bad idea because the reason you're doing the assignments is so you learn the material for the midterm and final. If you just let someone else do the work, then you haven't learned it. So don't do that. I mean, you can do it. I'm letting you collaborate. If you say that, okay, fine. I mean, each paper, now, when I say work together, acknowledge it, you still should write up your own things. Your assignment should not be completely identical word for word. You should have written up your own individual answers. And, we might, get upset with you, if you do that, but don't shoot yourself in the foot. I'll be putting things up on the wiki. I'll show you the page. We'll have the course. There'll be course notes there. There'll also be the lecture notes. There is a textbook. This is operating system 3 easy pieces. If you want a PDF of it, you can. If you want a one PDF, you can pay for it. You want a hardcover or soft cover, you can pay for it. But the chapters are all here as individual PDFs, and you can download them for free and look at them. So you don't have to pay anything for the textbook if you want, but I will tell you this, the textbook is not the sole authority for this class. I consider the textbook to be a supplementary reference. Read it when you have questions on concepts I've talked about, and what I'm saying doesn't quite make sense. But to follow what we're doing in this class, start with the tutorials and what I say in class. That's what matters. This is what you go to for more depth or for slightly different treatment of things. I'm not going to follow the textbook exactly at all. And I'll explain that that's actually a big thing. So, we're going to be working with, okay, I'll fix that later. We're actually working with Ubuntu this time. What's that? And so, acronym advisor, you know this. Okay, I've told you about that. Plagiarism. The reason why I want you to give credit to everyone who can help you with your assignments is because that avoids plagiarism. I know where you got your work. Academic accommodation, disability, religious. Basically, I take all of this as a very simple thing. I won't be a jerk if you won't be a jerk. If you require accommodations that are reasonable person says that you've got something going on in your life, and not even necessarily according to exactly these categories. I mean, just stuff happens. And if stuff happens, if I can reasonably accommodate you, I'm happy to. I care about you coming in, learning the material, doing your work, and getting through this class. And sometimes people need a little, some accommodation for it. I'm perfectly happy to do that, but just don't jerk me around and give me sufficient notice. I mean, it's like asking for, I need more time with this assignment after I've already accepted assignments and submissions have closed and I've posted the solutions. No, don't do that. Oh, one last thing I don't think I mentioned. With the tutorials, you can complete the tutorial work up to the midterm or final, which means that the tutorials that are covered for the midterm need to be completed before the midterm. And the tutorials for the final need, of course, need to be completed by the last day of classes. So if you want credit. So don't, and that does not mean come to a TA the day before the midterm and say, I need credit for all my tutorials. I did them all at home. Please give me marks. Because otherwise I'm going to lose 10% of my grades. No. Do not put them in that situation. That's really annoying, and don't expect them to accommodate your silliness.
Generally, is it possible to finish the tutorial during, or will you force it in advance to start working?
The tutorials, oh, so that's the question. Can you get through the whole tutorial in the time of the tutorial time? In general, no. You can get through part of it. You can get at least started. I do not expect you to, so that's actually a really good question. I do not expect you to go to a tutorial, spend an hour and a half, 80 minutes, do it and go like, I'm done. If you manage to understand everything and get through it, fine. And for those who have some experience here in Linux and stuff, some of you will be able to do that. That won't be a problem. But others of you, especially if you aren't so familiar with Linux, you have not been hacking on your own, you're going to need more time. Things are going to confuse you. And you need to spend the time to figure things out. The purpose of the tutorial time is to make sure you get started, to make sure other people are around and the TA is there to help you with the initial bumps. It's not that that's all the time you need to spend on it. This is a question, yes?
Will tutorials be made available prior to the date?
I'm going to try getting them available. So the first tutorials run Monday and Wednesday. I'm going to try getting them done before the Wednesday class before. So you should have the tutorial for next Monday by this Wednesday, because I want to talk about it in lecture before all the tutorials. And that next Wednesday, so this Wednesday I will start talking about the first tutorial. So we'll have this cycle of Mondays will probably be more theoretical and Wednesdays will probably be more based on the hands-on material for the tutorials. Other questions? So that's the boring stuff. Let's talk about the reason why we're all here. Might as well put the leading 0, why not? So to start off, is that big enough? Can you see that in the back? Or is it a little too small? It's good? Okay. So what is an operating system? Because this class is called Operating Systems, and we're going to talk about it all semester. It makes sense to spend a few minutes at least talking about what the heck is an operating system. Anyone else? Come on. Some of you must have an idea. I like people to say things when I ask. Not in the middle of what I'm saying something. That can be annoying. But what's an operating system? So an interface that acts as a conduit for conduit for controlling resources. Okay, yeah. That's so the classic. So classically, what's an operating system do? It's about resource management and abstraction. Those are the two basic things that we're talking about when we talk about an operating system. But what I like to think of is it's the software that turns the computer you have into the system you want to program. That's a very expansive definition. By that definition, lots of things like middleware, you could say a web browser kind of falls into this. Maybe parts of a library, but I think it actually captures a lot of what an operating system is, because, in fact, there have been entire legal proceedings over what an operating system is. Back in the 90s, Microsoft argued that Internet Explorer was an integral part of Windows. Does anyone know why they argued this? That it was part of the Windows operating system.
Because Netscape was trying to say that it was unfair competition for them to release an internet browser for free?
Yes, because Netscape was arguing it was unfair competition. And the unfair competition argument was about bundling. Because one thing that because Microsoft was seen as having a monopoly in the PC operating system space, And one thing monopolies are not allowed to do is to use that monopoly to leverage their existing monopoly to get another monopoly. And one of the ways you do that is by bundling things together. So Netscape argued that Microsoft was unfairly bundling a web browser with their operating system, and since it was tying the two together, that was giving them an unfair advantage. They were also doing price fixing, dumping. They were basically giving away for free, where Netscape wanted to charge money for it, all these things. Now, of course, sitting here a couple of decades later, what do we have? Web browsers are all free. Every operating system includes its own web browser. And in fact, it's a key component. And we have entire systems that require the operating system to provide it. Or maybe it's not the operating system, but entire classes of applications that depend on having a web browser bundled with it. Not just web applications, but say the entire class of Electron apps. Those bring a web browser along with them. So why am I saying all this? Is that an operating system conceptually is a fuzzy thing. There's a lot, if you say, what is an operating system? Is that an operating system? Is that not an operating system? You can get into a lot of funny semantic arguments. And that's not what we're going to spend our time on here. I'm going to talk about something very specific. We're going to be talking about something called Linux. And Linux is actually kind of a funny thing because when you say Linux, technically you're not saying an operating system. What it really is, it's an operating system kernel, which is a very important part of an operating system, but it's not the only thing that makes up an operating system. And in fact, if you go to some people, such as Richard Stallman, they will say that you should not call something like Ubuntu Linux. You should call it GNU Linux. Why do you say? You want to see a fun argument. So I haven't defined what a kernel is. We'll get to that shortly. But whenever you see the term GNU Linux, it's basically saying Linux by itself is not an operating system. You have to have a lot of other things with it. The GNU project produced a lot of these things, so call it GNU Linux. That's an interesting philosophical argument. What does a name mean? But suffice to say, we're going to be talking about Linux, GNU Linux, whatever, in this class. And before I talk about what it is, I'm going to talk about why it matters. Why should I talk about this? I'm going to talk hardly anything about Windows. I might make some passing references to it. It turns out conceptually, Windows, while it has certain key differences, it's mostly very similar to Linux. Mac OS, iOS are mostly very similar to Linux. Systems like QNX or Minix have certain architectural differences, but then they also have a lot of similarities as well. What I want to, but even with all of that, why this? Why is this the right choice, I think, for a class? I think it's been the right choice for a long time, but it's particularly a right choice, I think, in 2018. Anyone know why? The answer is actually pretty simple. The world runs on Linux. It's taken over. It won. And when I say that, I mean it's everywhere. Okay, your desktop might not be running Linux. But if you are running a modern version of Windows, you can run Linux binaries on it. There's an entire subsystem. So the Linux as a kernel is so important that Microsoft implemented the API in Windows. So you can take Linux binaries and run them directly on Windows. Directly. Not like there's a copy of Linux there that's running underneath it. No, directly on there. You might go, why did Microsoft do this? Because they had to maintain their share of, basically to maintain their developer mind share. They want developers to build things on Windows. And if they're going to build things on Windows, they have to be able to build Linux applications. And that gets to the real important places where Linux matters, and that is the cloud. The cloud runs entirely on Linux. That is the infrastructure. That's what everything runs on. Will it be the case going forward? We'll see. There's some arguments where I think it may stay really strong, arguments where it might not, and we can talk about that later. But right now, the cloud runs entirely on Linux. I mean, anytime you connect to a web service, almost certainly the operating system underneath it is Linux. Unless, like, it's maybe if you connect to a Microsoft service, it's not going to be running Linux. But otherwise, basically, it runs Linux, which is kind of crazy. I mean, there's millions and millions of computers that are running this software. And then everyone's, if you're running an Android phone, it's running a Linux kernel underneath it. Your smart TV probably runs Linux. Your, streaming stick, you name this device, all the IoT stuff, so much of it runs on Linux. So this is a world you should be familiar with. If you are a computer scientist of any kind, this is a world you should understand. Is it because is Linux so popular because it's free? No. That's part of it, but that's far from the only piece of it. And the reason why, so Linux is an implementation of an idea. And the idea is Unix. And I think, and the reason Unix has taken over, because when we say Linux has taken over, what we're really saying is Unix has taken over. And Unix took over because it's always been there. The internet, because what's taken over the world is the internet, and the internet was created on Unix. So what do I mean? So when I say Unix, that actually refers to something from the early 1970s. There are some guys over at Bell Labs, who were hacking around with a PDP-11 and said, we need an operating system for this thing because we really don't want to be programming this entire thing in assembly language, based without any sort of support utilities. We need something to abstract this, to turn it into the computer we want to program. And so what they did was they made a little operating system. And when they named it Unix, it was a pun. Does anyone know what the pun was based on? Unix is supposed to be a castrated version of Multics. If you look at Multics, it's an operating system of the late 1960s, which was basically supposed to be utility computing. This was the operating system that was going to run the world. And they had all kinds of features. This was a mainframe operating system. But the ideas of Multics were very powerful, and a lot of them influenced Unix, and even the ones that weren't initially there got added on later. But Multics was big and complicated. And it was really designed to kind of do everything. And Unix wasn't. It was designed by these couple of guys going like, let's have fun programming. And they get, first version they programmed in assembly. Like, assembly's really annoying. And we want to make it portable. We want something efficient. So they made something to help make things portable. You know what they made? C. The folks who invented Unix invented C. And those two are right there. So C was developed, Unix was developed the same place, and then they had to give it away for free because of another legal impediment known as the Department of Justice going to Bell Labs, going to AT&T in the US and saying, you're a monopoly. You're a monopoly on telephony things, so we do not want you using that to get a monopoly in computers. So you write software, you better just basically give it away to anyone. So they did. They made Unix, they gave it away basically to universities for almost no licensing costs and let them do whatever they want with it. So they licensed it to a place called Berkeley. And Berkeley said, so folks at Berkeley, the folks in the Berkeley, I forget the name of the group, but this group at Berkeley had a contract to develop the networking protocols for something called the ARPANET. And so what they do, they took that Unix thing and hacked on it and added networking support because Unix didn't have networking. And they implemented BSD Unix, which was what ran the early part of the internet. And that formed a little company you might have heard of called Sun. They took BSD Unix and commercialized it and made workstations for it. And Sun in the 1980s said the network is the computer. And they were the ones who were, other folks were pushing the internet. Unix was there the whole time, and many variants of Unix on many different workstations came along, but they were all commercial. Linux just happened to come along at the right time to ride the wave of the web exploding and people needing a free version. You might say, well, why didn't BSD Unix take over? Because wasn't it free and didn't they have something? Well, there were lawsuits that happened in the early 90s. Where a lot of the BSD code was tied up and the people who created it got sent to court. Basically, AT&T said, we want our money now, and claimed copyright infringement. So BSDs were kind of held back at a very critical time, and Linux wasn't. It was a clean room implementation, and there were some differences in licensing, and then Linux took over. So really, accidents, licensing, laws, and making programmers happy. Whole bunch of factors. So anyway, Linux is everywhere. You better understand what it is. And that's what we're going to talk about. Now, one thing I've got to talk about, though, this term is I'm going to do one thing differently. You are welcome to go back and look at my old tutorials. You're welcome to look at my lectures. They're actually still up. But this term is going to be different. And the difference is one thing. I'm a security researcher. I study system security. And I realized after teaching the course last term that everything I was talking about could be talked about in terms of security. So this is an operating systems class, but this will also be an operating system security class. Because I realized almost everything that's in a modern operating system is there actually for, in part, security reasons. That if you don't consider security, most of it doesn't make sense. And if you understand where things are going to go, you have to understand security. So we're going to talk a lot about that. So along the security part, I have to give you a little introduction to security. So what's the key idea I want you to understand before you understand anything else? Is the idea of a threat model. The idea of a threat model is that every defense you create has limits. There's no such thing as a defense that defends you against everything. Like, let's say you use the best encryption to protect your data on your computer. Is your computer now safe against a sledgehammer? No, it's not. You have not protected it. So in order to evaluate a defense, you have to understand what types of attacks it's designed to protect you against. So what threats? So threat modeling is very specific to security. But in general in computer science, we have what I call problem models. So anytime you develop part of when you think of any problem that you're trying to solve, when you create a solution to it, you're assuming that the world has a certain structure. Like you say, oh, do you have the data necessary to solve that problem? So if you look at an operating system, you're really looking at a set of problems that are having to be solved. And I will say a lot of the problems that are trying to be solved are actually threats. And we'll start with kind of the basics of the threats. I think the most important thing to think about is what happens when a program crashes? So that's a funny thing. When I say a program crashes, it means program misbehaves and is shut down. This is something that is routine to all of you. You use computers with many programs on them. Some of the programs can misbehave, and when they do, you can terminate them, and the rest of the system is perfectly fine. This did not used to be the case. If you go back a couple of decades, early PCs, the Apple IIs, the Atari 400s, 800s, or even if you go back to the old mainframes and stuff, a lot of computers in history, when the program that was running on it crashed, the computer was dead. That was it. You had to basically restart the entire computer. One program terminating, causing problems, meant the whole computer down, because really the computer only ran one program at a time. And then there were systems that said, well, no, I want to run more than one program at a time. But those programs would know about each other. They would work together in such a way that if one of them messed up, still it all broke, because they weren't properly separated. So at a basic level, when you go back to things like MS-DOS. They are operating systems They're not modern operating systems. And I use the term modern operating systems, even though it really goes back to the 60s, is because a modern operating system, so we'll say yes. So things like MS-DOS, you could call them an operating system in the sense they provided device drivers because they would allow you to have files on disk. So you didn't have to know exactly how data was encoded on disk, whether it was a hard drive or a floppy drive or whatever. You didn't have to care about that. You just knew you could write files to it. And there was code, MS-DOS, which would abstract away from that and give you an interface for it. And you could even change the kind of drives and devices and stuff, and it would still work. So in that way, it is an operating system. It's a disk operating system. That's what DOS stands for. But it's not what I'd call a modern operating system because it had no support for running multiple programs safely. When I say multiple programs safely, I'll be very specific. There were these things called TSRs. Does anyone know what a TSR is? I'm just curious, show of hands. Who's heard of a TSR? Almost nobody. Okay. So, so a TSR stands for terminate and stay resident. So in the days of MS-DOS, when you booted up a program, it took over the computer. Yet DOS was technically in memory, but really the program you ran, whether it was a game or a word processor and stuff, that was really the only thing running. But people kind of went like, oh, these computers, as they get powerful, I'd really like to do something else. So, let me see. Sidekick. Do they have that still? Oh, Borland Sidekick. Oh, this was, so you see this? Let's see if I can get a nice little view of this. So what you could do, you see this? It has time planner, notepad, file manager, phone book, or something. So and you notice there's a C prompt here. So what you could do is you're sitting there in DOS or in a word processor or something, and you hit a special key sequence. I forget what the key sequence is, but you hit a key sequence, and then this would pop up over whatever it is you were doing. And you'd be able to say, oh, I would like, take notes, or I'd like to see my calendar, or I'd like to see my phone book or something. All these kind of useful things that I might want while I was in another program. So you hit that key sequence, and it would pop up. So you go, hey, that's MS-DOS. Multiple programs are running. You got this cool little Sidekick thing running, and you have your main stuff. But Sidekick was doing black magic in order to do this. When you hit that key sequence, it was basically intercepting a very low-level hardware event from the keyboard driver, and then calling its code and basically freezing the program that was running, and then took over. So this is what the TSR idea was. You would first run Sidekick, and so it would terminate but stay resident. It would still be in memory, and it would set up hooks so that when certain hardware events happened, it would be invoked. And when it was invoked, then it could pop up and pop on the screen and let you, bring up a calculator or something, and you type it in, and then you'd hit another key sequence, and you'd pop out. So escape. You'd hit escape, and you'd go back. And you're back to wherever you were. But that was really flaky. I mean, you do this, and most of the time it would work, but then some programs wouldn't be compatible with Sidekick, and they'd crash, or, other ones that wouldn't run. It's like, no, it's like, I want to be able to intercept that. It was a mess. It was a mess. And what if you want to run another one of these things? What if you have some other cool little utility that you want to pop up and run in the background? Because it turned out there were a whole bunch of these things. Oh, they would conflict with each other. And they came up with standards for how they wouldn't conflict with each other, but basically they all had to play nice, because if any one of them messed up, the entire system was dead. So just imagine, you just hit a key sequence to look at a calculator, to calculate some things while you're typing up your, a term paper or something, and the calculator crashes, and your word processor crashes, and you lose all your work. Exciting, isn't it? So that's bad. So that's bad. But it actually got, So TSRs, they did let you do a little bit of this. But there was one nail in the coffin that just killed this as a way of doing things. I just said, this is just not going to suffice. And that was the internet. The internet killed it. And the internet is the reason why everything has to run a modern operating system. For a simple reason. So my computer right now has to deal with me typing on this thing and whatever demands I'm making of the computer, and it has to deal with the network. On this computer right now, I have an Ethernet cable plugged in. I could be using Wi-Fi, same difference. Anytime data comes over the network, it has to be able to receive it. And then it may have to send it out. And when I say send it out, it may send it out, and then it finds that it can't send it, or it got lost, so it has to retransmit and stuff. This all has to happen in the background while it's also dealing with me. It has to be able to rub its belly and tap its head at the same time. And if it messes up either of these things, bad things happen. People implemented networking stacks on MS-DOS, and they were a disaster. Amazingly flaky. You do one, you look at it sideways and everything crashes. So you can run a web browser on MS-DOS, but it's just does not work that well. It's just not, well, I tell you, people have made it reliable, and the way they make it reliable is basically the web browser takes care of everything. But again, that's all it's doing. My computer right here can do a million things at once, and actually has been for the past, you might say, oh, my computer today is really powerful, but hey, 20 years ago, 25 years ago, and go to the internet, even 30 years ago, could do multiple things at once without problem. Multiple programs running at the same time, some of them talking to the user, some of them talking to the network, some of them doing other things completely, all of them working in harmony. And if any of them decide to misbehave, they get terminated, and the rest of the system keeps on running. That's what makes a modern operating system. What do you need to pull off this trick? Think about it, it's a pretty simple thing. If you're going to run a bunch of programs and you want them, you have to figure out how you're going to allocate resources between these programs. How are you going to deal with the program that misbehaves? When you say a program crashes, what it really means is someone told the program to terminate. It was killed. So who tells it to? So someone. So you have to have someone to be in charge, someone to allocate resources. So the part of the system in a modern operating system that does that resource allocation, that does that basic resource allocation and dealing with errant systems is the kernel. Now people talk about microkernels and monolithic kernels and other things, and there's all this, there's architectural things, but the idea of a kernel is it's the program in charge. It's the boss of the system. So the problem with MS-DOS, with the terminate and stay resident, is no one was in charge. There was no program to boss everyone around. Everyone considered themselves to be equal. The word processor thought it was in charge. Then Sidekick came along and thought it was in charge. And they all had to work together, and no one could referee it. And DOS just sat there in the background saying, hey, call me when you want to write to the disk. You know, it's providing a service, but it's not arbitrating access to resources. In a modern operating system, a kernel does that. So when a program misbehaves, it's because it's violated the rules set out by the kernel. And when those rules have been violated, then it takes care of the program. If it's just a minor violation, it might just send in an error message. If it's a major violation, it terminates the program. So the kernel is the dictator of the system. So it's important to understand, MS-DOS was a democracy, you can almost say, or more anarchy. A modern operating system is a strict dictatorship. There's someone in charge, and every other program runs at their sufferance.
So MS-DOS did not have a kernel then?
So it does not have a kernel. MS-DOS does not have a kernel in a modern sense because no program is in charge. There was, you can say there's the MS-DOS kernel, and they would refer to it as the center of things, but it didn't have any power. Other programs could actually overwrite its code, patch it live, and change completely how it behaved. It had no authority. So the kernel is what's in charge. And that's what makes a modern operating system, is that there's a program in charge of the system that can arbitrate disputes between programs. Unix is a particular design of how all these APIs and stuff there, but the basic idea, many systems do it. Windows has basically the same design. Windows NT forward. Windows 95 and stuff did not. And then, but then the question with kernels is, how do you have one program in charge? How can one program be in control of the whole system? Well, one program has a high ground. One program's in charge. Which means that so think of, let's say I had someone sitting at the, let's say I had someone sitting at the door that was controlling who got into the room. And the first person sitting there going, I don't know what I should let or not. And then I come along and I tell them, only let in people who are wearing a blue shirt. If they do not have a blue shirt, keep them out. So I tell them that first. And then they'll start controlling access. Now, what if someone else comes along? Now, you should only let in folks with, or then I tell them, don't listen to any instructions from anyone else. Anyone else gives you an instruction, ignore them. So then another person comes along, only let in people with red shirts. And don't listen to anyone else. And go like, hey, someone already told me not to listen to anyone else, so I'm not going to listen to you. So now, still the blue-shirted policy still comes along. This is basically what happens with your computer. The hardware So at a high level, what happens is the processor on your system starts off in a mode that allows access to everything on the system. The kernel boots, and then it says, I get all of this. But anyone else who comes along, they only get what I tell them to. So it then sets up the policy for how resources are going to be allocated. And the hardware enforces that policy because the kernel came first and basically said, it's mine. It claimed the hardware. And thus, everything after that has to follow. Now we get into the first bit of security. Does this policy how safe is it? So I'm saying the rules that decide what programs are allowed and what programs are not allowed to run on your system are determined by what code runs first on your computer. I'm saying, is that safe? Is that really safe? Or is that kind of like, what if someone got there early and said, no, it's not blue, it's orange? Or what if they said, allow in people with blue shirts, but only 20? Now coming here, I was expecting a lot more people. And then all of a sudden, now it's like, the first guy thinks, oh, they're letting blue shirts, everything's working fine. And then all of a sudden, things stop. Or I said, let in people with blue shirts, and then once everyone with blue shirts is in the room, shoot everyone. It's like, you could do that. I mean, the notion of the first one to come along is the authorized party to give instructions for what to do is not necessarily a good policy. And in fact, we have learned this with modern computers. So actually, modern computers don't do this. They have another policy. They check credentials first. They see whenever who comes on first, it's like, okay, yeah, I think you're first, but show me your ID. If your ID is okay, then I'll let you tell me what to do.
What checks credentials?
The hardware, what checks credentials? The hardware checks credentials. And specifically, if you want to go into cryptography, what it means is it checks to make sure the code of the kernel has been digitally signed by the appropriate authority. And the authority is whatever's been built into the hardware or was initialized in the hardware. Maybe instead of the first boot, then it's like whoever got to it and put the keys in there first. So most motherboards, by default nowadays, only boot kernels for PCs, only boot kernels that have been signed by Microsoft. This includes Linux. So in fact, most modern Linux distributions, their kernels have been signed by Microsoft. Now, it is possible to go into a PC settings on one of our PCs and change it so it will run unsigned binaries. But you have to change that setting. So you would still potentially be able to run Linux on those systems, but you would have to go in and configure the BIOS and say run unsigned binaries, or give it a key that is used to sign the Linux kernel and then run that. So you know your Android phone has a locked bootloader? That's what I'm talking about. A locked bootloader is just something that there's a set keys that are checking the signature on things. And so if your code isn't signed by the appropriate key, then you can't do it. And who has control of those keys? The hardware manufacturer. So unless you run an authorized kernel, you can't boot your code on there. That's why you can't run alternate versions of Android. And certainly that's how it works on iOS devices. Apple strictly supports that. Classic PCs didn't check that stuff, but now most hardware does in some way. On PCs, you can fiddle with this. You can change which keys it trusts, or the systems are signed. The authority that does the signing is widely, is more permissive in what they sign, but other things, they don't. But the reason this matters, the reason why this is so essential, is because the first code that runs gets control of the hardware and sets all the policies because it's the kernel. It's in charge. And every program that boots after that has less privilege. It has to follow the rules that are set by that first code. So going forward, but now, okay. So let me draw a little picture here. So the bottom layer, we can say we have hardware. And you can say the operating system, we have here, sitting above it. Then on top of this, we'll say, okay, so I might have something like Firefox, or let's see, operating system to itself, So you'd have and other, so you have applications here running on top of it, and they're logically all running. Enough of my ASCII art here. So you have a web browser, you have a text editor, you'd have a terminal, you have whatever. They're all running on, you could say logically, on top of the kernel. And what that means is each of them communicates with the kernel directly. And in particular, the resources they have access to are determined by the kernel. They have to ask the kernel to have access to the hardware, and then only then can they access it. This is how you keep things safe, because in effect, the hardware is when these programs run, they only have access to limited resources, And if they want more, they ask the kernel. And if they try accessing resources they don't have access to, they aren't authorized for, then a message is sent to the kernel, and the kernel decides what to do with them. It either says no, or it decides maybe just to go ahead and terminate them. It's up to the kernel. It decides what happens on policy violations, but the hardware is what tattles on them. So that's the division of responsibility. In a sense, the hardware is this very powerful, it's like it's a powerful entity that accepts commands, but it doesn't have any sense of morality. It doesn't have any sense of what's right and what's wrong, what should be allowed. All of that is determined by the kernel. It determines what is allowed and what's not. So let's say I run, so the question now, let's put some names to this. So a running program. We call that a process. If you run a program, if you run it in a process. You can run the same program multiple times, but each instance of the program will be a separate process. So when the process wants to request something from the kernel, those requests are known as system calls. So those are the key terms we're going to talk about. We're going to talk about processes, talk about system calls, and talk about the kernel. Now, a system call you can think of as you can say a system call looks like a function call. But, and from a programming language level, you might think that you're, oh, this is just like a function call. In fact, system calls are often wrapped in function calls. But semantically, a system call is a very, very different thing. And it's very different because of a key idea for making the separation. These different processes all think they have an entire computer to themselves. They each have what's known as they think they have their own memory and they have their own processor. That's what they think they have. They don't. What they have is, in effect, they have virtual memory and a virtual CPU. But they can't tell the difference. They just have their own processor and their own memory. And why does that matter? Because what does a function call rely upon? So the basic way you make a function call is the basic idea of a function call is it's basically like a goto. You're just jumping to an address, but you leave some things behind. So you remember where you are in memory, you put all the arguments that you want for the things to be processed, like, oh, what's X, what's Y, and then the processor, you do a jump to the address of the function. The function runs, and then terminates, and then it pops the address off there. I will talk about function calls more later. Actually, how many of you are familiar with this when I say how a function call works? How many of you feel like, okay, so this, I was kind of thinking from 2401 you should have a basic idea of this. But the thing to understand is when you call a function in C, you're calling the function name. That name gets translated to an address, just like every variable gets translated to an address. So a special instruction is used to call a function where you where it records where you were and then jumps to that memory location. And then when that function terminates, it just pops off the stack saying, oh, this is where we were, and goes back to where you were. Why this matters, why I'm talking about this, is in order to make a function call, you have to be able to see the memory of the code, the memory containing the code and data. You have to be able to see where the function is. You have to be able to see, the same variables. You have to be in the same address space. You have to be able to see. You have to be able to talk about the same things. That doesn't work here. Firefox cannot see the data that's in Emacs. It can't see it at all. They're completely different address ranges. If Firefox refers to address 2000, it's completely separate from address 2000 for Emacs. So, given that it has its own isolated memory map, how can it call the kernel? And even worse, if it were just to jump to the kernel's code, it doesn't matter if it's the right kernel code. The CPU's in a mode where it won't let you have access to all the resources of the system. You can't talk directly to the hardware. You can't, you can't do anything except for what you could before. So it's not enough just to jump to the code. The CPU has to take on more privileges. It has to switch modes. So a system call looks like a function call, but underneath it's very, very different because, yes. Now, I'm not expecting you to understand what that means right now completely yet. Some of you will completely understand this. Others of you will be going like, I don't know about this. Don't worry about it. You're going to see a lot more about this. This is kind of the high level, just sort of trying to fit this together. And the last bit I want to talk about in relation to this is security. Because here's the key problem that you have when you write an operating system kernel. Processes are going to make all kinds of requests to you. And the thing the kernel has to do is it can't trust any process. It has to think they're all out to get it. So every system call has to very carefully validate every request to say, is the requester authorized? Is this request properly formed? If I incorporate this, will I accidentally overflow a buffer or something? I mean, there's all kinds of problems that could happen if you give it bad data. So the kernel has to be written in such a way that it checks everything that comes from there. Think about the last time you wrote a function. Did your function check every possible bit of data that was sent to it and made sure it wouldn't mess with it? Most of the functions you wrote did not work that way because it's a real pain. It takes a lot of time and a lot of effort to check the data coming into every function. But the kernel has to do that on every system call because it can't trust regular programs. They could be messing with it. And those checks are expensive. So system calls are things that you do because you have to do them. They are inherently more expensive than function calls because you have to do constant checking for errors and for security. So anything that you want to implement as a function in your own address space. You call the operating system, you call the kernel, when you want to do things that you're not allowed to do because it's not safe or it's not secure. So understanding that boundary and understanding what is in your process and what is delegated outside that's what we'll be talking about during the semester. But I want you to think about before the next lecture. Just look at the devices you run. Look at the things that you play with on a day-to-day basis. Think a little bit about how many programs I'm interacting with right now. On systems that you can, look at how many programs are running. Run Task Manager, run PS, run Activity Monitor. See how many things are running. And then look at how many resources they're using. Which ones are using more resources? Which one's running less? Someone will tell you how much battery power they're being used. When you look at those things that give you an accounting of what programs are running, you are getting a report from the operating system kernel on your device that's telling you how resources are currently allocated and being used. And now, the question then you should ask is, how did it tell me? How did I get that information? We'll talk about that next time. Thank you.